Anybody go to Bourbon Festival last weekend? No? It makes no sense to me. Just curious. You're still down? I just find that, like, if you're the kind of person that drinks bourbon, you don't really need a festival. It seems like you can just go drink bourbon. Yep. One more second. Still seats up front. It's not church, you guys. Not gonna bite. Okay, I think just about time. Yep. Okay. Hi, everybody. I mean, I know it's the last talk, and it's been a long weekend, but hello, everybody. Good enough. I'm here to talk to you guys today about GNU Radio. You can download the slides there. I give another link at the end of the slide, though, if you miss it. So, everybody, my name is Mog. I, kill gremlins, fight video games, and my own best friend. I like to solve problems, especially simple ones. And does anybody know what the acronym means? Just out of curiosity. I'm trying to. Huh? No? Close though. It means I am not a doctor, so I am in no way an expert on anything. I'm a tinkerer. I like to work on projects, but do not take anything I say today as dogma. These are just my own personal experiences, and I'm trying to pass them on to you as best I can. And so, yeah, just this guy. So, what is radio? It's black magic gobbledygook. Somehow you have power, it comes in or out of an antenna, it flows through the air, makes twists and turns, does crazy stuff, has all these words associated with it that no one will understand ever, including engineers who tell you they do. It's like the insane clown posse says. You can't explain it. So, what I will say radio is it's information that is in the air. And so that's all as deep as I'm going to go into the actual science of how radios work. It's just a way of getting information from me to you using passing it across a vacuum. And so what is GNU Radio? Well, clearly it's a software-defined radio system. But what does that really mean? It just means GNU Radio is a way of taking information out of the air and bringing it into a system, into a PC, or a way of taking a PC and putting information into the air for someone else to receive. And so that's how that's what that is. So the first to understand, you have to, before we had software-defined radios, we had conventional radios. So anything from a TV set, your car radio, ham radios, radar, everything. You end up with devices that were very low power because they were very specialized. They were only designed to do one thing, and they did it well. So they would only work on their frequency range. They would only decode the type of signal they were looking for. And because of that, they were also very cheap. Because they're just doing their one job, and they do it really well. And so for most things, that actually is the right way to solve the problem. You want to build things cheaply. You want them to be efficient with their power usage. And you want them to do whatever the job you assign it as well as possible. But the problem is, what if you don't know what you want to do? It's the same reason why we have software for solving most of our world's problems rather than building hardware devices that solve them. It's because software is so much more flexible, and we can react to problems much faster. And so a software-defined radio is basically the opposite of a hardware-defined radio. So it's flexible. Typically, it will work over a large range of frequencies, can deal with different amounts of bandwidth, has different, and it's just flexible. It can do just about anything. One of the other problems with it, though, is it's very inefficient. So a software-defined radio will always use more power, more CPU time, more memory, all of your resources than a hardware-defined radio. And the other thing is, because of that, it's expensive, not just in all those ways I just mentioned, but also just price. The cost of components, the complexity of your system, it just adds to price. It's always going to be more expensive, at least for a single radio to a single radio comparison. So for a lot of consumer devices, it probably is a long way off. And so this right here is just a screenshot of GNU Radio Companion. It's a simple flow graph, and I'll go more into that soon. But it's a little daunting, so we'll take it back for a second. So this right here kind of defines what a radio looks like. You have the antenna, which absorbs the signal from the air. The bandpass filter is how you filter out the noise on either side, so you're just getting the signal that you want. Your gain stage takes this weak electrical signal and makes it much louder so that you can actually see the signal easily. Your mixer and local oscillator is how you get things on a clock sequence so that things are coming in order that you expect. And then your ADC converts the analog radio signal into a stream of ones and zeros that the computer can understand. And then the DSP is how you analyze that string of ones and zeros and turn what could be like FM radio into actual audio out to your speakers. And so in a software-defined radio system, it's divided up twofold. Typically, you have the hardware side, which is everything on that side, and then you have your software side, which is just the digital signal processing, and that's in the PC. So you'll have a device like an RTL SDR, an EDIS software-defined radio, hack RF, some kind of device to bring in the analog signals from the real world into the PC. And then you'll have a program like GNU Radio or AirCrack or several other programs that will analyze the data coming in and making it into something meaningful. And so, like I said before, you have a lot of hardware options. The first is this guy, This is a TV tuner card that they sell, and it happens to have a radio inside of it that you can hijack and use as a software-defined radio. It ranges in frequencies from around 30 megahertz to 2.2 gigahertz with a few holes in the inside, and you get 2 megahertz of bandwidth out of it, and it is ridiculously cheap. You can get them on eBay for like $30 or Amazon for around that same price. The one downside of it, though, is it is only designed to receive signals, so you cannot transmit with it. The next option, next step up, I would say, would be a device like this. This is a HackerF1. It's an open source piece of hardware. It does receiving or transmitting, but not simultaneously, so it's what's called half duplex. And it works on signals from 10 megahertz all the way to 6 gigahertz. So that's pretty much anything most people want to play with. You got, like 900 megahertz phones. You have 2.4 gigahertz Wi-Fi signals. You have 5 gigahertz Wi-Fi signals. You have the cell phones that are in the 443 megahertz range. You have a lot of remote control stuff in 27, 55 megahertz range. A lot of useful bands that this can interact with. And then there's another device called the Blade RF, which is kind of like the next, I would say in some ways the next step up from the HackerF, in that it's full duplex. It's a little bit more expensive, and it covers a little bit less range, but 300 megahertz to 3.8 gigahertz pretty much covers most things people want to tinker with, I think. And so it's a good option as well. Then there's the first people that kind of like pioneered this market was Edis, and they sell very expensive, very high quality software-defined radios that are typically used in education markets, but not something a hacker would buy. And there are actually many more now have entered the market. There are a lot of options for hardware to interface with. And so the first thing I tend to recommend to people is just get an RTL SDR. They're very inexpensive, and you can figure out if you're actually interested in this. So with it, like, you can break it out of the box. You can listen to FM radio. You can listen to like the NOAA alert weather radio. Just like very quickly, kind of just play around with what signals are in your area, and it's fun tool to get started with. Then the next thing I tend to recommend people is just get a HackerF, because now you can transmit some stuff, you can see more signal, and it's not that much more expensive. And then if you really need to do full duplex, I think it's best to just get another HackerF, because you can use 2 HackerFs in tandem to have a full duplex radio stack. And so you're not wasting any money. You've just kind of added to your collection. Although it is a bit more clunky to have them tied together, I guess. An optional thing that I also recommend for people, especially anybody that has a ham license, are these little Baofeng radios. They cost almost nothing. I think I got this for $20 on Amazon one day. And it's an FM radio that does 136 to 174 and 400 to 480. So it's useful, especially when you first start off with like your HackerF. You can broadcast and you can actually see it on a real radio and listen back. And that's kind of cool. So the next step, so you got your hardware. You're ready to start receiving signals from the real world. And so you have some options for software you can play with. The one I'd recommend everybody always start with is a program called GQRX. It gives a nice kind of front end that lets you see a waterfall of all the signals coming in and lets you just kind of quickly like play with some real radio and capture signals. SDR Sharp is a very similar kind of program. It's used a lot on Windows. I don't use Windows, so I don't know a whole lot about it. There's a program called AirProbe that's pretty cool. It uses your SDR, and it allows you to see the GSM traffic and decode it to a degree. So you can see people's unique identifiers, for example, and you can tell like who's around your house, which is kind of cool. Web radio is a nifty kind of tool. It gives you with a few lines of Python, you have a web interface to your SDR. So when I was on the road a lot last summer, I set it up so that my SDR was listening to the baby monitor, and then from anywhere in the country, I could go to this web page and I could hear the baby monitor, which was pretty cool. LTE scanner is similar to AirProbe, except for it's for LTE phones. And then finally, GNU Radio. GNU Radio is the Swiss Army knife for doing everything. So let's get started. So I really recommend using a GNU Linux installation rather than doing this on Windows. Although most of the tools exist in Windows, I think it just works better and more easy inside of Debian, for example. It's very easy to install the software you need. It's just one line, apt-get install these pieces of software, and it'll work for you. So the first thing I was going to show y'all is, right now I have, this is a HackRF as well. It's just a fancy case for it to try to filter out some noise. And I have it plugged into my machine, and we're going to show you guys GQRX. So this is GQRX, like I was talking about before.
Have a
14-7
lead over the Falcons.
I've tuned the radio to 93.918 megahertz, and I'm telling it to decode it as FM signal.
He's been efficient.
And
Jerry Jones
I've made the window of what we're listening to this. So if I go wider,
73 yards to start the game.
You can't really hear it over the speakers, but there's a little bit more noise. Like if I shift this off the signal. Oh, I have the threshold low. That's why. Here. This is going to be loud. Oops. Wrong way. So yeah. So that's the noise. It's just background radiation noise because there's no channel there. And as so right now, my radio is absorbing, the PC is processing this whole 8 megahertz bandwidth. So from, I guess, 91.5 all the way to 98.5 is being decoded on the PC right now. But we're only actively listening to this one 500 kilohertz section. And as I slide it over, it's just instantaneous.
Bengals have a 7-0
hear the radio station coming
on the road.
And what's
Baltimore
cool
Ravens,
is,
another 0-2 team, desperately
unlike just like a normal radio, you can go
year.
anywhere. So if I went to 2.4 gigahertz, so if I go to like 2.410, you'll see it better. So that whole hopping up and down, that's the Wi-Fi traffic in the room. It's bursts around 20 megahertz. So we're not seeing the whole signal right now because this is just on an 8 megahertz window. But those blips are all Wi-Fi packets. And this software isn't set up to decode it, but you can see that it's there, and then you could go into GNU Radio or other tools and start to figure out what you want to do. So this software is really good for just kind of getting a feel for your area and seeing what kind of signals are just floating around you. Yes? Oh, okay. So this is an artifact of the way software-defined radio works. It's the DC offset spike, as it's called. It's always there. It's always in the center of whatever frequency you turn. And so the way to work around it is you actually, like how I'm tuned in on an offset of it, you always offset to the offset, one way or the other. So if I wanted to listen to that station, which was like, what was it? So like if I wanted to, let's see, that's 94. So if I move this to 94, it's really hard to see that signal because it's right next to the offset. It's kind of being lost. And so the way to always make sure you get your signal is you'll want to shift this off a little bit and then hit the signgle. So it's just a defect in the way the process works. And it's a problem with all software-defined radios. It's real easy to work around like that, but it's
never good when you look down and you go, hey,
just something you have to be aware of.
Had to come out, put it out. and rectify the situation.
And
Steelers
what
on
others?
top
Nifty
of
stuff.
the Rams 3-0. 5 minutes to go in the first
That's
quarter.
pretty much this software also has the ability to actually record the raw samples coming in if you wanted to like take it into another program later. But I find it's just most useful for just kind of like looking around you and seeing what's going on.
Take care of business
And
against
it's so easy to just use. It's just a matter of opening it, basically. So that's GQRX. And so listening to a radio is pretty cool, but it's really nothing new. I mean, we all have radios, or actually, I don't think many of us even have radios anymore. So let's make one instead. So for this, we'll actually have to go into GNU Radio. And let me see if I can make this look better. Can I get this all on one screen? So what this is a GNU Radio program written in GNU Radio Companion. And I'm not sure how well... Can you guys read this at all? Okay. So you have this, the way it's kind of outlined, you have some blocks at the top. These are just like the variables that are being set for the program. So like, for example, the audio gain, how loud the sound is going to be is just set, to 1. What channel we initially tune to. Oh, wait, this is the transmit. Wow, cheated. Okay. So basically the same. We have the frequency we're going to tune to, how wide the channel we're going to listen. So like before we were listening to at 500K. This time we're slightly narrower. We're at 200K. The volume that we're going to play it back at, and what frequency we actually are going to hit. And then below here is where all the work is really done. So the first thing, we have 2 main kind of block types for getting information in and out. We have sources and sinks. So because we're going to be absorbing radio in this instance, we're going to take it into from the source, and then we're going to do a few functions to it to massage the data, to get it into an audio signal, and then we're going to put it into a sink that's the audio sink. And so just at a high level real quick, what we do is we do a low-pass filter, which filters out, like I was saying before with the hardware side, we filter out everything above and below, everything above what we actually want to hear. Then we resample it to the bandwidth we want, and then this is the magic bit that understands FM radio, or FM signaling. And that's really all there is to it. So when I show this to you guys, if I could compile and run it. So it's very similar to the other program. I have these 2 blocks come built in as well. This is a waterfall and just an FFT. Basically what we were looking at before. And then I think the station was 94 that was coming in good. That's creepy. Oh, that's the center. So that right there, what we were listening to, that's the DC offset spike. And so if we weren't paying attention, we hit it and there's nothing there. So I think there's a signal at 100. Nope. So we'll go in here and we'll change our center frequency to be lower. So I think 95 should take us closer to the right spot here. So that's it. I don't know why. I think it's the settings here. Yeah, I have the R5 gain off. So if I come in here and I turn our gain on, we should be able to hear it. Because I had to turn it on over there because this building is hard to get radio through.
college graduate in my family. The first district attorney from my neighborhood.
And that matches
And
up
if
to
I'm
what
the
we're
first,
seeing here.
then maybe there will
so
be a
this is
second,
saying there's
and
a
a
signal
third.
right there.
This can
And so
really
that's
be
what
the start of
that's what we
something.
found.
My name is Charles.
So
and I'm
I understand I kind of skimmed over what all these blocks do, but a lot of this stuff is pretty straightforward. It's just it helps to understand a bit about like what signal you're trying to get. But I'll explain how those blocks work here. So the variables are like those blocks that don't actually have gates on either side, and those are set outside in the editor, like we were doing. So, for example, this is one variable that's in every program. Essentially, is the sampling rate, and it's what speed we're processing the audio at, or the signal at. And so, in this case, this variable was probably from an audio source because it's at 44.1 kilohertz, which is pretty typical for that. And then the most common type you see are these things called blocks. They tend to have an input and an output because they're just massaging data on its way to someplace. But then you also end up with like the sinks and sources where the endpoints are. But most of the blocks are actually just points along the path. So the data types that it knows about are all listed there, and so that's why when you go over here, that's what all these colored endpoints mean. So it's light blue, which means it's a complex float, and the orange one means it's a float 32. And so all the blocks, the data types have to match. And what's nice is the language has all these converter types. So you can convert any type to any other type, just like you would in any other programming language. So now that we've listened to FM radio, wouldn't it be much cooler to broadcast FM radio? And the nice thing about that is it's actually even simpler than listening. So to build something that will broadcast audio, it's pretty simple. You have to give it a source of information. In this case, I'm using a WAV file I made, and then I have this multiply constant block because I want to have the ability to apply gain to it. So the multiply constant is currently 1, but it's taking a variable of audio gain, so that when if I adjust this slider within the program, it'll make it louder. And then here we have this transmit block, which takes the signal and FM modulates it. Then we have this rational resampler block, which converts this 88.2 kilohertz FM signal, puts it in the center of a larger signal because the hardware can only broadcast out at a 2 megahertz sample. So we have this 2 megahertz sample we're broadcasting with this small signal in the middle of it. And this sync here is just so we have, a GUI to what we're doing. And I made it repeat. So right here, we are transmitting at 165 megahertz. And let me auto scale. And so right in the center is where our song is. And does anybody want to guess what the song is? Has something to do with September 22nd. Nobody? Okay. On September 22nd, no, you're not going to hear it. It's the Happy Birthday song. Happy Birthday finally entered the public domain, or didn't actually enter the public domain. The copyright held by Warner Brothers was rejected. And so it's now ambiguous if you can sing the Happy Birthday song, but I say you should do it. Because no one owns it right now. And so that's what this is doing. We can adjust where it's broadcasting at by just sliding the frequency around. And we can adjust the volume, and it'll get louder. It's kind of hard to see on this because the the scale, but it got louder. No, I can't. Yeah, you can see it right around the center. The peak is wider, and so that's how you build a transmitter. Yep. So another project, or not really a project, but there's so many fun things you can do with this that a lot of them are pretty easy, like the FM transmitter was. So this July 4th, my family got together and we had this boat race with these little remote control boats. The fun thing about them is they operate at 27 megahertz and they just broadcast a simple FM modulated signal that says, go forward, go back, go left, go right. And so I took one of the remotes and I just listened to it for a bit, and I started off boats. So here I have basically kind of two programs combined. I have this one program that's the grayed out program, means that it's not active right now. And so I had my HackRF set at the frequency of the boat, and I brought it in, and then I just wrote down all the information I received to a file. So what I did was I took the remote and I hit, the controls forward, and then I wrote that to a file called forward, and then I saved that file, and I changed it backwards. And so then I had copies of the signal for the boat going forward, going backward, all the different states of the boat. And because the boat was so simplistic, you didn't have to do anything. It was just a replay. You could just replay the information back, and it would confuse the boat. And so I set it up to keep repeating go forward 2, which caused the boat to turn a little bit. And I just raced with all my brothers and won every race because their boats kind of just drifted, and they couldn't figure it out until my little brother got frustrated and dropped the remote, and his boat kept going, and they kind of caught on. But it was fun while it lasted. Lasted for a good bit. But it was real straightforward, easy to do. But it's really easy to build these more complex programs because you're really just building these flow graphs that are pretty simplistic. And inside of GNU Radio, you get all of these blocks to begin with. So you can do AM, FM, ASTC, DVB, MFSK, TCP, UDP, GSM, ULAW, ALAW, codec 2, blah, blah, blah. Tons of different ways you can get data in and out of the software. And what's even cooler is, you guys know what CPAN is? Anybody? Yeah, the Perl library. There's a CGRAN for GNU Radio, and so people have written modules that integrate very easily in. So like there's RIDI, ADBST, OP25, Bluetooth, Bluetooth LE, different cell phone technologies, Zigbee, Wi-Fi. So it's really easy to take any one of these blocks and integrate them into your own code and work with it.
So like Bluetooth does like frequency shift type thing. It's like
Yeah. So what's great about in particular the HackRF is a lot of those the moving of where the frequency hopping, they still do within a small domain. So the Bluetooth frequency hopping, I believe, is, I want to say it's around a 20 megahertz window. So the HackRF can receive a 20 megahertz window. So you just absorb the whole window and you follow it. And you can see it all. The other way around that, if it's a bigger window, there's two kinds of attacks. You either learn the protocol enough so that you can follow the frequency hopping as well, because you can change your frequency window typically as fast as whatever is doing it as well. Or you just build a big enough system that you can absorb all the signals. So one of the projects some people did with the GNU Radio community early on was the police scanning. So police scanners work on a frequency hopping system over, I think, like 16 megahertz. But people at the time just had these guys, and these guys just absorb a 2 megahertz signal, which is really only wide enough for a single channel of what they were doing. And so what there were kind of two attacks people did. One attack was people got 10 of these, and they just chained them in, and they absorbed that whole spectrum, and they just got it. And then somebody that was more clever reversed the protocol enough to where he could have two of them, one that watched the control channel and would listen to where it was supposed to go, and the other to change all along the way. So the next program that I kind of worked on, has anybody heard of Gotenna? I think it's like the niftiest project in the world, except for that it's proprietary. It's this little VHF radio that does an encrypted signal over VHF to Bluetooth low energy to your phone. And so their idea is that you can send text messages without a cell phone network within a smallish area. So like at concerts, or if you were going rock climbing out in the middle of nowhere, you could keep in touch with people that were in your group with just text. But what intrigued me was it was encrypted and was kind of wide range. It's in around a few miles range. It's using this protocol called MERS, or a standard called MERS, where you're allowed to. Turns out it's the only one out there that's for citizens, where you can encrypt your traffic freely. And so I thought that was really cool. And so I wanted to kind of build something similar to it myself. And I got working on, I didn't want to do text though, I wanted to talk to people, because it's lame to text people in the wilderness. So what I have here is kind of a more complicated program. I used one of those blocks from CGRAN that I was talking about called GNU Radio SALT, NaCl. It's the same Python SALT library that's gotten real popular lately for doing crypto. And I also used something that was built into GNU Radio called Codec 2. It's going to sound a little bad, but it's at 3.2 kilobits a second. Kilobits a second, yeah. So it's really small. And so the way this one works is similar to our FM transmit. We have a file coming in, and I'm throttling it out to this sync so we can see the sound file as a visual representation. And then another thing, here, we're shifting it into a data type. This is like I was talking about before. I'm changing the data type from a float 32, casting it down into a short. And so I'm kind of throwing away some of the data and compressing it, but having to lose some of the data in doing that. And then I use this Codec 2 audio encoder, which just converts the uncompressed wave file into this small codec. Then we vectorize it and turn it into a stream. So this is kind of like packetization of it, or this is massaging the file so that it can go into the crypto stack. And then after it's out of the crypto stack, it gets traded into a packet. And then from a packet, it goes to GMSK, which is a frequency encoding model. Typically, this is how a lot of data gets sent through the air. You'll hear it sounds like modem tones, kind of, when you actually listen to it. And so what's nifty about this program is this is just a test program I wrote, so I actually never go into the air. This is all just done on the PC. It never leaves the PC. So to use GNU Radio, you actually don't have to have any hardware, only if you actually want to transmit to the world. And so then I'm basically doing the exact opposite process. So I'm converting it out of GMS and K, taking it out of a packet, running it back through the crypto, converting it from Codec 2 back to regular audio, and then converting it back into a float, and then back out the audio sync, and then I'm running it through this FFT block again, so we can see how the audio has changed once it's passed through this whole process, because it's like MP3 encoding in that it's not friendly. It's going to change the sound. So this is me singing Happy Birthday, converted into Codec 2, encrypted, and then converted back out.
Happy birthday to you. Happy birthday.
So this is at 3.2 kilobits a second, which is really small, transmitted a long way over VHF. And although I don't think anybody would want to listen to that, it's certainly intelligible, and it's unbreakable except for the fact that the key currently is A, B, C, D, E, F, G, H, I, J, K, L, M, N, P. The kind of obvious key, but that could be fixed. Do it in post. So I guess, does anybody have any questions? Yes? Yes, so one of the cool things about GNU Radio is when you compile this, let me see here. So docs code GNU Radio. What was I just doing? Salt test. So GNU Radio companion is actually just an interpreter directly into Python. So this salt test, the GRC file is what we've been looking at, but every time I hit compile, it generates this Python block. And the way to do it without a GUI, so like if I come here and I just do user bin, I want to get the right Python. Yeah, it's angry at me. Oh, because it can't find the test file because I'm in the wrong path. So let me cp / So that's just run directly from Python. So if you didn't want it to have a GUI, you would just take out, so we have this one top block that instantiates a GUI, but you can actually change this to say no GUI, and so then you don't have a GUI, and then you just don't call any of these like FFT, the pretty GUI functions that I was using. And so then it's just a command line based thing. And that's how some of those other tools I talked about were actually built, like the web radio tool is actually just a GNU Radio compiled file that doesn't have a GUI. Yes? Satellite radio. So one of the plugins, like XM radio is encrypted, so you can't get that. But there are different satellite systems that are free to air, and there are people that decrypt them. I mean, not decrypt them, but unencode them with this software. There's support for ASTC and NSTC, different transmission schemes that people actually still use. That's pretty cool. Yes?
When you were doing the buttons, they were all on that same frequency.
So they actually, many of them say they're around, when they say 27 megahertz, they're not actually at 27 megahertz. So it was actually like, his was actually at 27 megahertz exactly, but mine was at 27.5 megahertz. They're all stamped that way, and they're all made really cheaply. So I think we had like 4 boats, and 2 of them were on the same frequency because they just don't care. Because it was like $8 boat. Yes?
The GNU companion software, does it have debugging tools?
So there are, so there's some blocks here that kind of can help with that. There's like message tools where you can like do like kind of printf statements as things are going by. And then like, for example, if you actually have something that's broken, so like if I disabled this block, it has a smart enough thing to already tell me that this won't compile because throttle is pointing to nowhere and every block has to terminate to run. And then this has its own compiler that will tell you why things break, if you break things. But you can also, like I said before, how it's just Python, you can run this in Python and see why things are breaking. But I would say it's pretty easy to debug stuff for the most part. What makes it hard about debugging stuff is, especially if you're working with another system, you really, when you're starting off with your attack or your, and understanding what you're working with, you really want to make sure you get captured. There's a plugin called File Sync, and you want to copy whatever you're listening to so you can replay it within the system itself, because you don't know when something will transmit again. And so that can be really frustrating. Like, there's a train track near my house, and when the train comes by, they actually signal about half a mile ahead of time, hey, I'm a train, I'm going to come by, you should shut the gate pretty soon. And I thought that'd be really cool to have like some way to alert me, like, don't go that way because the train's going to be there. But it took me forever to get anything working because I had to listen when the train came by, and it's before the train comes by that signal is sent. And so I had to set up something to log all that data for a long time before I had a clear signal that I could actually interpret. Any other questions? Huh? So no, it's actually it's pretty clever how they do it. The signal for lowering is I don't think is actually in the air. I think it's just for things to know that it's coming. I don't know why it's not triggering the actual gate. I think that gets triggered mechanically, I would guess. But that's scary if that's true. And maybe that's part of why it's not done that way. Some extra resources. There's a subreddit called RTLSDR, which is a good place to start if you're just starting. GreatScottGadgets.com/SDR. He's the guy that makes the HackRF. And he has some videos that go actually in depth about how some of the physics and stuff work, but no one understands it. There's GNU Radio on the Freenode network. They're really helpful people there. It's a really cool place to hang out. And all the code that I've displayed today is on my GitHub page. And FCC.io. So this is the coolest website, especially if you're trying to reverse engineer something. Anything that has a radio in it, they have to provide the FCC with copious amounts of information about how the system works, like what frequency it's at, just anything you want to know. And FCC.io gives you an easy way to search and find the product that you're actually working with, and you can get tons of information right off the bat. It's a very cool website. I didn't know where I was going to put this slide. This is just the frequency allocation from 3 kilohertz all the way to 300 gigahertz. So this is how the government has divided up the spectrum. It's kind of ridiculous. And it's my contact information and how to get the slides, if anybody needs it. Thanks. I hope everybody enjoyed Derbycon.